Hi, I'm Joshua Bowers, and I will be discussing the correlation between population density and number of cases of Ebola on both the district and chiefdom level, as well as spatial correlations between chiefdoms and districts. In this first figure, you can see 6 graphs. In the left column are the graphs that show the total number of cases. On the right column are the graphs that show the total number of cases plus the suspected cases. The top row represents the total population. The middle row is just the male population, and the bottom row is just the female population. Each graph is comparing the population density on the x-axis with the number of cases on the y-axis. As you can see, as population density increases in all different populations in both the suspected and the confirmed cases, there is an increase in those cases. And so there's a correlation between a positive correlation between population density and number of cases. The actual R values can be found in the upper right-hand corner up here. And if we're curious to see data points that look like outliers, we can hover over them and see, for instance, in this case, that the Western rural has a low population but has a disproportionate number of cases, whereas another district like Bow has quite a high population comparatively, but lower cases, and it is an outlier in a different direction. When we look at this on the chiefdom level, we can see that the correlation is completely non-existent. We have some chiefdoms that have a very large population, but almost no cases, and some chiefdoms with very small populations with many, many cases. In this figure, we can look at a spatial analysis of the number of cases in a district versus the number of average cases of its neighbors. So essentially, this is telling us that if you had a lot of cases for your population, you're far to the right on the x-axis, how likely were your neighbors to also be experiencing the same thing? We can also again break this down to the chiefdom level, and the correlation disappears almost entirely, with many of the chiefdoms experiencing disparity between them and their.
Okay, so my name is Max Green, and I'll be talking about developing a tool to extract and examine 1 gram frequency time series from the natural language responses to some of the questions on the Ebola survey. So the 4 graphs shown here just represent the frequency time series of 4 different words. The frequency values are relative percents, meaning that the y-axis is calculated by taking the number of times that the selected word was used over, the total number of words used during a given time period. And here the words are binned at the month level, and the time series lasts a full year, running from December 2015 to from December 2014 through December 2015. And we'll notice a few things here. The hope or curiosity is that these frequencies can be reflective of behavior or incidences in the real world. And we'll notice that some of these timelines link up with some of the reported incident timelines from the actual event. During the outbreak of Ebola, we're seeing a spike in Sierra Leone, and then a subsequent sort of downward trend. And the same is true for hunger, fear, and food. One other interesting piece of analysis that we can do is incorporate a geographical component by stratifying these frequencies across different districts. And so in particularly, if we look at this graph that looks at the frequencies of death, it's possible that some of these spikes that happen in particular regions at particular times could indicate, where there are concentrations of, conversations about death and perhaps more, death events themselves. And so, this could be a tool to possibly use in the future in real time for as a component of an event detection system. Thank you.
Bag of words TF-IDF approach. So what I did here was I pulled in the data from the trigger data set as well as the follow-up data set, and just took responses to every single question, put them all into a single corpus for each visit. And so we see here that each visit to each community has a corpus, and then that's been broken up into 1 gram, so single words separated by a space or punctuation. This step doesn't actually have any data cleaning involved, so it's very much a rough pass, but with a data cleaning step, I believe this could be pretty helpful. So what we do next is a TF-IDF approach. So it's a measure of the originality of a word, comparing the number of times that word appears in a document, in this case a single community visit, with the number of visits that word appears in overall. And so we train these vectorizers both at the chiefdom level and at the district level in order to get out these data frames where, in this instance, we have all of the chiefdoms as the index, and the columns represent every single 1 gram. What we can see down here is, as expected, there's kind of a Zipfian distribution to the word frequencies. 2 is very commonly used. The of Ebola actually is up there with most function words because of the content matter. Is and no, community, dead, and body, hand, sick. And so some of these words we would expect to see in a normal corpus. Some of them are pretty divergent because of the subject matter. So going over to the mapping portion here, first what I did was just map the per capita death counts by chiefdom. We didn't really have enough time in this project to do a full-scale data cleaning process, and so you'll see that this map here is actually missing quite a few chiefdoms, but for the ones that we have, we can see higher per capita counts. So we have per capita death counts by chiefdom and district, and then another thing that we can do with mapping is actually look at the district level usage of any 1 gram. So this is the district level usage of the word Ebola. This is district level usage of the word burial. We see that this district actually has a much higher instance of the word burial in responses to all follow-up and trigger questions. And when we nail down to the chiefdom level, we can actually see this particular chiefdom is kind of driving that hotspot on the map that we're seeing. So that's burial. This one is looking at usage of the word community. Interestingly enough, I found this 1 gram anti-disestablishmentarianism. Of course, this scale is much lower than the previous scales that we've seen, but we can also see those values both at the district level and then at the chiefdom level. So this could be an interesting tool in that we can search for any 1 gram and see the TF-IDF scores by chiefdom and district. Hopefully with more data cleaning, we could see all of the districts and chiefdoms on these maps. But this would allow us to kind of drill further down into the lexical patterns in the communities that are most affected.
For this part of the project, we're going to look at topic modeling for the data sets. This will pull out salient features of what the people of Sierra Leone were talking about during the Ebola crisis. So what you see here is a topic model on the follow-up data set where the people of Sierra Leone were asked questions about the biggest changes and concerns they were facing. So overall, here are the top 30 most salient terms, and each of the terms used were a trigram or grouping of 3 words in a row. And a lot of them you see here mention the school, community, and laws. And there are more topical features here that we're facing today, like hand washing and talking about soap and water. For this topic, I want to point out a couple of interesting terms that were being talked about. The 4th on the list is about controlling teenage pregnancy. And for that one, that was a big concern about teenage pregnancy rates increasing during the Ebola crisis. Here, they also mention community and schools. And what happens here is a couple of the concerns are about how schools closing seem to show an increase in pregnancy rates among teenagers. In the trigger data set for a topic model, I wanted to point out one interesting feature. This top one on Rely Liberian border is about this one community in particular who depends on food imports from Liberia. So there's issues on food scarcity as well during this Ebola crisis.
Hey, this is Brendan. I'm going to be talking about a risk model I built with this data. So this uses the follow-up data set, and basically it's looking at the average number of seriously sick people per day, and reduces this to a binary, either positive cases were found on that day or no cases were found on that day. So this results in the following sort of matrix, where each chiefdom across the rows here is sort of turning on and off whether or not there were infections detected during that sampling event. The model we built to interpret this data is based on McKenzie et al. From 2013, and it's originally from sort of ecology, but I think it's going to be useful here as well. So at the top of the cartoon here, we have a Markov process, which begins with a chiefdom being infected with some probability gamma, and then you can either become uninfected with some probability epsilon or reinfected with some probability gamma. And finally, we have our true observations y, which is further masked from this true Markov process with some detection probability p. So some preliminary results from our model. We found a significantly higher colonization rate than extinction on those posterior distributions. We also found a detection rate of around 0.45, which of course could mean that detection is just very difficult in any disease collecting effort, but it could also mean that the extinction rate is even lower than we observed due to this distinguishability issue between whether there was really an extinction there or whether we just failed to detect it. So future work should do some things to try to get around this issue.